Sir, hindi pa siya man-initialize ng ano eh. Dun sa pag ano po, pag-initialize po ng array sa ano po, sa pointer po. Ito po, sir. Ay, sir. Ano po to, sir? Yes, sir. Sir, hindi po kayo nagsusstream. Hindi po. Yung screen niyo po. No, sir. Atas na pag-ano ko na po yung ano. Yan po, sir. Napag-ano ko na po, sir. Yes po. Nabago lang po yun. Tinanggal ko po yun ampersand sa ano. Sa pointer 1 po. Line 8 po. Ito po. Yung ampersand po nandito sa ano. Sino po gawa na po? Yes po, line 8. Hindi po siya gaano. Hindi po. Eh. Yes, sir. And Mm-hmm. Yeah. Good, sir. Yup. But, wala pang lalabas. Pa. Right, sir. Oops. Ah, shh. Ah, good sir. Yup. Uh, oh,
Hey everybody, we finally made it to dynamic memory. Dynamic memory is memory that is allocated after the program is already compiled and running. To allocate dynamic memory, we use this new keyword. It's an operator. It allows us to allocate memory in the heap rather than the stack. It's useful when we don't know how much memory we'll need. It makes our programs more flexible, especially when accepting user input, because we have no idea what the user is going to type in. Here's an example. We'll start with a basic integer variable, but we'll allocate memory in the heap rather than the stack by using that new keyword. I'll create a pointer. Int dereference operator p num. Now it's good practice when you declare a pointer, but don't assign it right away, to give it a value of null, meaning no value. To allocate memory in the heap rather than the stack, I'll take my pointer, set this equal to, use the new operator, then a data type. I'll use up enough space in the heap for one integer. The new operator will return an address. We're storing that address within pnum because it's a pointer. It's pointing to a memory location where we're going to store an integer. Later on in your program, whenever you would like to store a value, we can use the dereference operator, our pointer, then assign some value. Like 21, I don't know. Just for fun, I'm going to display the address that's stored within the pointer. Address p num, then I'll add a new line, as well as the value. Value dereference operator p num. Our pointer is storing this address, and at this address in the heap, that address contains this value, 21. Now it's very good practice, if not expected, whenever you use the new operator, you'll also want to use the delete operator when you're no longer using that memory space. So at the end of this program, or earlier if you choose, we will delete our pointer. Delete pnum. We're freeing up the memory at this address. If you don't, you may cause a memory leak, and it's best to avoid that. Whenever you use the new operator, you probably should be using the delete operator someplace within your program. Here's another example. We're going to dynamically create an array. Let's create an array of grades. Char, then we'll need a pointer, dereference operator, p grades. Set this equal to null if we're not going to assign this pointer right away. Then to dynamically create an array, we will take our pointer, set this equal to new, the data type, char. If this is an array, we add a set of straight brackets. Within the straight brackets, we will list a size. If I have 5 grades to enter in, I would type in 5. But if we already know the size of the array before we even run the program, we might as well do that normally, like create a normal array. There's no point to allocating memory dynamically. We would want to do that when we don't know what the size is going to be. So I propose we ask for some user input. Let's say int size. We'll create a prompt. Standard output. How many grades to enter in? Standard input. Size. We'll dynamically allocate enough memory in the heap depending on how many grades the user has to enter in. I'll just create a for loop so that we will ask the user to enter in some grades. Int I equals 0. I will continue this as long as I is less than size. Increment I by 1. Standard output. Enter grade number I plus 1 because I will be 0 to begin with. And I'm just going to add colon space afterwards. Standard input p grades, that's our pointer. Now we can either add plus I or use those straight brackets at index of I, either way. Let's display all of the grades. Int I equals 0. I is less than size. I plus plus. Standard output p grades at index of I. I'll separate each with a space. And remember, if we no longer need this array, we should delete it to prevent a memory leak. If we have to delete an array, we'll add a set of straight brackets after delete, then our pointer. P grades. And let's try it. How many grades to enter in? So we don't know what the user is going to type. Let's say 6 grades. Enter grade 1, A, B, C, D, F, A. And here are the grades. So that's why dynamic memory is useful. It's memory that is allocated after the program is already compiled and running. We use the new operator to allocate memory in the heap rather than the stack. It's useful when we don't know how much memory we will need. It makes our programs more flexible, especially when accepting user input. So that is an introduction to dynamic memory. We'll have more practice with this in the future, so don't worry. If you would like a copy of the code that we worked on, I'll post that in the comments section down below. And well, yeah, that's an introduction to dynamic memory in C++.
Adobe Acrobat Studio is all new. What can PDF spaces with AI do to a sales invoice good enough to eat?
Hey there, hope you're having a wonderful day. In this video, we're going to continue the topic on pointers, and we're going to talk about memory allocation. So there are two main types of memory that you need to be aware of. We have static memory, which is known as stack memory. So this is memory that is allocated on the stack. And then we have dynamic memory, otherwise known as heap memory or free store. And this is allocated on the heap. So one of the main differences between the two is stack memory is allocated at build or compile time. So basically, when you want to run your C++ code, you have to build it first, and then you run it. So when we are building our C++ code, we are translating C++ into machine-readable code. So we're translating it into instructions. And at this time, there are checks for syntax errors and how much stack memory is needed. And basically, this is where all your variables and your function calls are stored. And we'll talk more about functions in later videos. And then we have dynamic memory. So this is heap memory or free store, and this is allocated during runtime. So unlike with stack memory, where you build your code and C++ determines how much space you need, heap memory is allocated when you run your program. So the heap memory is much larger than the stack memory. So for instance, let's say you are fetching emails throughout the day. You don't know how many emails you'll be getting throughout the day. So in this case, maybe it's better to store that data on the heap. And another example would be, let's say if you are playing a video game and the video game is constantly generating monsters and items. You don't know how many monsters or items will be generated because that might depend on how long the player stays in the game. So for that reason, maybe you would want to use the heap memory for storing those monsters and items. Alright, so that's just a brief rundown of the differences between stack memory and heap memory. Now let's write some code to illustrate the differences. So let's say if I create a variable for my savings account, we now have a variable of the type int, and this is created on the stack. And I can also assign it a value. So I can do savings is equal to 10,000, and this value 10,000 is also stored on the stack. Now, if I wanted to create this integer on the heap, I would use a pointer. So pointers allow us to reference memory addresses that are stored on the heap. So to create an integer on the heap, I would do int star, and let's call it savings pointer. And here I would write new int. So new is a keyword that allocates memory on the heap. And of course, with pointers, we are pointing to a memory address. So this saving pointer is actually a variable. So pointers are pretty much variables that are assigned memory addresses. So the savings pointer is stored on the stack, but the memory address that it's pointing to is created on the heap. So with pointers, if I want to assign a value at that memory location, I would have to dereference the pointer, and then I can assign a value. So let's say I want to assign 50,000. So let's go ahead and print the two values. So over here, I'm going to do cout, address of savings, and savings. And then down here, I'm going to do cout, savings pointer. And then let's get the value. So I'm going to dereference savings pointer. And let's put endline over here as well. So now let's save and run the program. And as you can see, we have the variable savings, which is stored in this memory address location on the stack, and it has the value 10,000. And savings pointer is also stored on the stack, but the memory address that it points to is stored on the heap. So this is the memory address location for the value 50,000. And we can actually get the memory address of where that pointer is stored. So I can just do cout, savings pointer, like so. So I'm getting the memory address of savings pointer. So if I save and run the program, you can see this is where it is stored on the stack. Okay, so the variable savings and the pointer savings pointer are both stored on the stack, and this integer is stored on the heap. And with variables, I can also initialize the value. So I can just say 10,000 here, and I don't need to assign it here. The same applies for integers that I create on the heap. I can just do parentheses 50,000 like so. And then I won't need this line. So let's save and run the program. And you can see we get 10,000 and 50,000. So in Java and Python and other languages, there's something called a garbage collector, which frees up resources when they are not used. So in C++, because there is no garbage collector, we can accidentally cause a memory leak. So for instance, let's say I print this value out and then I want to change the value. I can do savings pointer is equal to new int, and let's make it 75,000. And then if I print out this new value, let's see what happens. So let's save and run the program. So you can see the memory address of the pointer is here, and it is still the same over here, but what we're pointing to is different. The first time when we create 50,000, we allocate memory over here. And then afterwards, we allocate another memory address over here, and we assign it the value 75,000. So what's happening here is we have a memory leak. And a memory leak happens when you do not free up the memory that is no longer being used. So even though the pointer is pointing to this new memory address, at this old memory address, this value 50,000 still exists. So at this memory address, we can no longer use it and we can't access it to clean it up because there's no pointer pointing to this memory address anymore. So this 50,000 is stuck there. So this is called a memory leak. And this can be very bad if you have lots of values that are created on the heap, but you do not clean them up. They still take up memory. So in order to free up the memory, we would use the keyword delete, and we would pass in the address. So pointers point to memory addresses, so I can just do savings pointer. And this will free up the memory where this 50,000 was created. So let's save and run the program. And you can see in this case, there's some optimization, and so the memory address is the same for these two integers. And that is because we freed up the memory using the delete keyword. So these two addresses are the same value. Alright, so that's how you can free up memory on the heap. And one thing to note here is that you should never do a double delete. So here we are freeing up the memory address. But if I do this, we are trying to free up the memory address twice. And this is going to cause an error in your program. So once the memory address is freed up, you should not call delete again. And one more thing I want to note here is that let's say I free up the memory, but I do not reassign the pointer. What happens here? So if I save and run the program, we have the pointer pointing to the memory on the heap, and it had the value 50,000. And then we freed up the memory, but now there's some random value here. And we don't know what this value is. This value could be a junk value, or it could be something that is being used by another part of the program. So this pointer, although the value is freed up on the memory, it's still pointing to that memory address location. And this is what's known as a dangling pointer. So a dangling pointer is a pointer that points to memory that we used to access, but we no longer have any need for. So we want to get rid of any dangling pointers. So in order to do so, we would just do savings pointer and assign it no pointer. So this is going to tell C++ that savings pointer is a pointer, but it is not pointing to any memory address at this time. So whenever you have a pointer that is pointing to a null pointer or a memory address that you do not have permission to access, you don't want to ever dereference and get the value at that memory address. So let's get rid of these two lines. Alright, so as a quick recap, we use a pointer to allocate memory on the heap using the new keyword. And once we're done with that memory address, we can free it up. And to do so, we use the delete keyword. So we delete and pass in the memory address, and this will free up the memory. And then we assign the pointer to a null pointer so that we do not have a dangling pointer. Alright, so that's it for this video. In the next video, we're going to